Okay. Good morning. So, in this lecture, we are going to talk about aseptic processing. Since this course is focused on emerging food processing technologies, I'm not going to discuss some of the conventional pasteurization, sterilization methods like canning, things of that nature. But those technologies utilize traditional conduction, convection heat transfer, and as a result, it takes longer time to process the food. Where while the canned products are quite safe, it degrades the quality of the product. As a result, the food industry has been looking for a better way to preserve the product quality. The second thing is canning is a batch process. So, that means you probably have a limited number of samples you can process any given time, and a lot of times the food processing industry always look for what I call continuous methods of processing, so that you can able to process them for a better quality, faster, and maybe much more economical. So, having some of these reasons, the aseptic processing has been looked at. Per se, aseptic processing is not a new technology. Even in 1960s, the concept of aseptic processing was developed and have been kind of tested, evaluated by many research groups. In the US, the Food and Drug Administration, which regulates and issue letter of no objection for novel processing technologies, require food processor to demonstrate the safety of the processed food using scientific methods. So, some of those required lot of scientific research and development. So, that took almost 1996 before the first aseptic processing for particles was approved in the US. So, in this presentation, so we are going to go through some of the basics concepts behind aseptic processing, some of the equipment associated with that, and then what makes the food safe, how do you validate the process technology, and other related topics. So, when you are sterilizing food, that means you inactivate all the vegetative bacteria as well as spore formers. You kind of want to increase the temperature of the product instantaneously, so that you kill the bacteria and the spore forming bacteria without damaging the nutrients. If you remember from the quality kinetics and the D values and some of the related data, remember that the nutrients are relatively more heat stable compared to the microorganisms. So, if you can raise the temperature quickly, you kill the microorganisms quickly without much contribution of damage to the say the nutrients. So, if you look at here, this is the spore destruction. This happens at 140, much shorter time, whereas this is the quality kinetics, where you can able to retain the product quality. If you look at here, much more retention of the quality is retained. Whereas at 121 Celsius, which is the traditional canning temperature, you are going to have almost a similar destruction of both nutrients and the spore forming bacteria. So, the concept behind the aseptic processing, can we raise the temperature very quickly to a higher temperature, 130, 140 Celsius, so that you can destroy the microorganisms without damaging the nutrients and the quality attributes. And traditionally, in the case of canning, you take the product. For example, if you want to make a soup, you prepare a soup and then pour the soup inside a say can, seal the can, and then assemble a set of cans, put inside a canning equipment, and then you're going to operate, and then you process for 30 minutes, 60 minutes, and then take it out, cool it down, all those things. Whereas in the case of aseptic processing, it's not a batch process, it is a continuous process. You take the product, so you prepare a soup, then you are going to heat the soup in a heat exchanger. So there are a number of heat exchangers, I think probably you may be aware of. One of them, for example, is tubular heat exchanger, where you have pumping the soup through a central tube, and then you have outer tube where the heating medium can pass through, thereby heating your soup. Or you can have a scraped surface heat exchanger, where you have a similar mechanism, but also you have an agitator which mixes the soup as it's being heated. Then you are going to cool it down, and then you bring into an aseptic environment. You take the package. So here it doesn't need metal package. You probably can have polymeric pouches, or you can even have a paperboard with some type of appropriate protection. So you can use some of those type of thing, and then you can sterilize them using some chemical or other means. So for example, hydrogen peroxide often used with some of the polymer sterilization. Then you are going to fill the soup inside your package, and then you are going to do that in a sterile environment, and then you seal it, and then your product is kind of ready. So this way there are a number of benefits. In a traditional canning method, you have to store a lot of metal cans. The metal cans maybe need to transport it from somewhere from the canning factory or some other place, and then you need to find a place for storing all those things. Whereas in this case, your metal, you are not using metal, you are using pouches. So those film stocks doesn't need to be pre-made, so you can probably able to store them much more economically. And then when your product is pumping through a continuous way, you are going to increase the heat transfer. So anytime, so simple example is, if you are boiling water in your kitchen, you just allow that to do that, it probably take a little bit longer. On the other hand, you kind of put a mixing spoon, or you put a spoon and mix it, it's going to boil quickly. So in the same way, in the product, when you are heating, you are pumping through, you are going to moving through at a particular velocity. So those mixing help to improve the heat transfer, thereby you can able to reduce the damage to the nutrients. So that's the concept behind the aseptic processing. So if you compare this is the traditional canning method, whereas if you look at here, this over here, you can probably have, this is a retard pouch, and then this is your HGST, your aseptic. So you're going to have much shorter come up time to reach the target temperature. So if you look at here, you may be reaching 120 Celsius, whereas that temperature can be accomplished much quickly with this, and then you can do cool it, hold it, and then you can do cool it down. And so this has a very short come up time, so that's way you can able to achieve much better quality of the product. Now, what is the criteria for making the product safe? So it's similar to canning. So canning has been practiced since 200 years or 150 years. So I think this lot has been established, particularly from 1900s. This lot of scientific data has been established. So what we are doing here is we are adapting some of those knowledge, time, temperature. You have certain log reduction of your target bacteria. So the target bacteria for thermal processing for sterilization is Clostridium botulinum, and then the target indicator organism or surrogate organism for sterilization is Clostridium sporogenes. So we use the same concept, except you are going to use much higher temperatures. And so if you compare here the criteria for returning versus aseptic processing, you can see that you can be able to accomplish much faster time. However, if you look at the calculation for the process, how much, where is the cold spot, how do you achieve microbial kill and so on, canning is relatively simple. So, for example, if I have orange juice and you want to do the canning of orange juice, you put a thermocouple at 1/3 from the bottom of your can, and then you measure the temperature, and then you deliver certain process temperature and time, and then you achieve sterilization. On the other hand, if you have a ham, which is conduction heated product, you put the thermocouple at the geometric center, and then again you measure the temperature for a certain time and so on and so forth. You can achieve that. So, these are all cold spots in during canning processes. When I say cold spot, this is the least treated portion in the canning process. In other words, if you have any microorganism in that cold spot, if they survive, it can give outbreak. So, you want to avoid that. So, this is relatively straightforward and people have done over many years. On the other hand, in the case of aseptic processing, especially when you have liquid and solid mixture, the process calculations can be much more complex. And if you have, looking at the energy efficiency, canning is more energy intensive. Part of the reason is you take, for example, certain energy, create a steam, and then there may be steam loss along the way, and then you deliver in the canning equipment, and then that in turn heat your product, and so there is going to be a lot of wastage of steam. Whereas, in the case of aseptic processing, that is much more energy efficient. So, that is again one of the attractions for this technology. And then you are going to have, this is another reason, if you look at why canning is still very popular or commonly used. If you look at the handling and labor, it is relatively high, but I think the people have the canning equipment, whereas the aseptic processing equipment, the labor cost is low, but the equipment investment is high. So, it is kind of, you have to make a business decision. Do I invest large amount of money for the equipment and then followed by less money on the labor cost, or do I just use what I have and then try to work with what I have. So, there is kind of lot of trade offs. So, when you look at some of the technologies, you have one side the scientific decisions, the second part is the business decisions. Sometimes these are not very straightforward. So, there are complex things can interact with each other. So, what is the aseptic processing, how the equipment layout looks like? So, you have a product tank and then you have a pump. So, this is the pump here, and then you are going to pump this through a preheater followed by final heater. So, let us suppose I have some tomato soup and I kind of take that and then pumping it, and then you are going to preheat. So, when I say preheat, you may take the product, the soup may be initially at 25 degrees Celsius, then I am going to preheat maybe 70 Celsius. So that you kind of not expose the product to very high temperature immediately, whereas in the second heater I may be preheating to 140 C. So that the heating occurs a little bit gradually rather than just immediately, because there are products which may be heat sensitive or heat shocked. So, you kind of want to avoid that. Then you have a holding tube. So, remember we talked about placing a thermocouple in the geometric center or 1/3 from the bottom and measure the temperature and see whether the product reached the proper temperature, so that you have indication of sterility. That function is done here in the holding tube. In other words, what happens is, if you have a product with the liquid and solid, you are going to pump through a holding tube. Holding tube is nothing but a simple stainless steel tube where the product is flowing through, and it may not be even insulated, but while doing here it has a certain length. So, from the entrance to the exit, it takes certain residence time. So, in other words, if you have a 5-meter tube and you are flowing at a certain velocity, it may take 30 seconds. Maybe if you increase the tube length to 10 meters, the velocity and the holding time going to change, all those things. So, you want to look at how much time I want my product at this temperature for how much time. You kind of have a calculation for whole tube. Based on that, you decide the length of the whole tube. So, this is kind of assure the sterility of the product in the aseptic processing system. Then it comes to the pre-cooling system, final cooler, and then you are going to aseptically package the product under those conditions. So, this is kind of very overall schematic of the aseptic processing system. If you later on we will talk about microwave warm heating, what you will see that the concept looks very similar. You are going to have a raw material tank, you are going to have your holding tube, your cooling heat exchangers, and then aseptic filler. The difference is this heater is replaced. This is a more traditional tubular heat exchanger or scrape surface heat exchanger. In the case of microwave, you may be using a microwave heater. In the case of warm heating, you are using a warm heater. So, the concept for aseptic processing can be adapted to warmic or microwave, and then you can be able to achieve products same. Later on, when we talk about pulse electric field processing and high pressure processing, there are continuous methods which also employ very similar approach, but they also use similar type of concept, where this section is replaced by appropriate heat exchanging unit, and then you are able to achieve the process. Now, I think we are going to go through some of the components of the aseptic processing system. The first is a blending vessel. So, you may have soup. So, you kind of want to hydrate all the starches or whatever material, and then you can able to blend them, bring them at the same uniform temperature. And then you are going to have a timing pump which control the product pumping at a constant rate. So, what that means is, if you look at this pump here, normally what they use is a positive displacement pump. So, if you are studying food processing, you probably might have heard about pumps. There are two broad classification of pump. One is a centrifugal pump, another is a positive displacement pump. Centrifugal pump are inexpensive. They deliver the product by centrifugal force, but they can have a variable flow rate. So, in that means maybe 1 minute it may be delivering 3 gallons per minute. In second time it may be deliver 6 gallons or 5 gallons per minute. So, flow rate is unpredictable. The positive displacement pump, something like here, they are going to be much more expensive, but they are going to have a precise temperature control or precise flow control. So, if I set my flow rate as 3 gallons per minute, it is going to deliver consistently 3 gallons per minute. Why we are using a positive displacement pump? Because of this holding tube. Because in the holding tube, you want your particles spend the same amount of time. So, in other words, if I target residence time is 30 seconds, we expect all the particles, all the fluid in the system going through that 30 seconds processing time. If I have a variable pump, then the flow rate may be vary. So, in one time it may be 30 seconds, another time it may be 60 seconds, another time it is 20 seconds. That can put your food safety risk. So, here you are kind of trying to keep the consistency. That is where the positive displacement pump is kind of used, and they call that as a timing pump, metering pump, and there are different varieties of pumps that are available. And you can use the centrifugal pump as a positive pump when you add what you call VFC, variable frequency drive. So, this control the variability within the pump and then make it consistent. So, instead of if you are going to have 3 to 6 gallons per minute flow rate change, then VFA drive kind of modulate that and then try to consistently deliver some constant flow rate. Now, there are different heat exchangers available. One is the direct steam infusion, or steam infusion, plate heat exchangers, tubular heat exchangers, scrape surface, ohmic heating, microwave. If you look at plate heat exchanger, this is more commonly used when you do pasteurization of milk. Here the plates kind of held tightly together, you have a very light fluid passing through. So, this is kind of where that particular heat exchanger used. In the case of aseptic, you may be using particles like liquid and solids particles. So, normally we do not use this heat exchanger here. Typically, you may be using tubular heat exchanger. So, basically you have a tube, you have product is going through your food product, and then you are going to have what I call the heating medium going in the outside. So, this is your heating medium. So, thereby as the product moving through the heat exchanger, it is going to heat. The scrape surface heat exchanger is going to be similar, but inside here you are going to add another rod, and that rod has some type of scraping blade. So, that when the fluid is passing through, this rod is going to rotate. It is going to rotate at certain RPM, and it is going to scrape the surface, interior surface of your heat exchanger. Why we are doing that? So, for example, when you process protein products like maybe starches and so on, when you are heating them, the material can deposit and they kind of form what they call biofilm or something along those lines, and they can reduce the heat transfer efficiency. So, to facilitate removing some of those things and also facilitate mixing, you normally use the this rotating mechanism. We will talk about ohmic heating, microwave heating in the next 2 lectures. So, steam infusion, basically you kind of have a product here, and then you have a steam, and then you are going to mix them in this zone, and then you have a product. So, steam has a very high latent heat. So, when it mixes with the product, it is going to instantly increase the temperature of the product, and then you have heated product comes out. One of the limitation of this approach is steam essentially water. So, let us say you have a soup with a certain consistency, you are adding steam, essentially you are adding more water to it. So, you are going to dilute that soup, and unless you recover that steam added later by flashing, it may kind of alter the quality characteristics of the product. Steam infusion is another version. Here you have product coming in, and then it is going to spray it here, and then this chamber has a steam, and thereby you are going to be able to heat. So, it is kind of have those two. So, these steam infusions, infusion as well as injection usually associated with a flash cooler, so that any additional water you added during the treatment could potentially removed. Whole tube. So, at the heart of the aseptic processing is the whole tube, because this is the place where you determine or demonstrate the lethality of your product. So, it does not matter how much time the product spent in the heat exchanger, you do not consider the lethal effect, only when the time it is spent in the holding tube. So, 30 seconds, 50 seconds, whatever that based on your thing, it is going to consider that. And then generally they are going to be slope upward 0.25 inch per feet, so that you can remove any potential air packet. And normally you monitor the temperature of the product at the inlet and the exit of the whole tube, and in the holding tube you are inactivating various microorganisms, bacteria, you may hydrolysis of starch and other things may happen, you may have caramelization of sugar, all those things may happen. Now, I talked about the aseptic processing temperature is 140, 130 Celsius. If you remember, water becomes steam, it boils at 100 Celsius. Whereas your product here being processed at 130 or 140 C. So, how do I maintain the product in the liquid stage in my holding tube? So, this is where a back pressure valve comes in. So, back pressure valve essentially you add some additional pressure to the whole tube, so that it increases the pressure within the tube. When you increase that, you are going to, your liquid remains a liquid, but at a higher temperature. It may be at 130, 140 Celsius, but it flows as a liquid. If you don't have the whole your back pressure valve, it's going to start flashing or becoming like a steam, and that can create a lot of problems. Other thing is, when you have a continuous flow processing methods, a lot of times when you formulate things, you may have air get into your product, and it's okay to have air in other circumstances, but in the process operation you don't want to have air, because air is a poor conductor of heat. So, that means your product may not uniformly heat. So, you want to add a deaerator to remove the air. The other thing is, air also have oxygen. Oxygen, when you do store the product for a longer time, it can affect the shelf life and quality of the product. So, you kind of add a deaerator so that you can remove the air, and it helps to reduce the fouling, and it can help to reduce the volatile loss, reduce the foaming, and then you can able to maintain consistent holding time under those conditions. Then once you process it, then you can able to dump all the processed product in a such tank. So, normally, you may be thinking, what is the capacity of such tank? You may be thinking 50 gallons or 100 gallons, but you may have 100 gallons to thousands of gallons capacity such tanks. So, these are humongous tanks, and so for example, you may be processing orange juice, you are getting fresh orange, and then you are processing orange juice using aseptic. You can probably process millions of pounds, and then you can store them in the such tank, and then you can bring them later to package them into small individual size containers. And then you are going to fill this in a consumer package in a clean in place type approach. So, clean in place, we will talk about cleaning and sanitation later on, but clean in place basically tells us your processed product is kind of packaged inside a pouch, and you want to that environment where that filling happens free from any bacteria. So, imagine you have a chamber, that chamber you are going to maybe pre-treating with UV or some other decontamination step, so that it is sterile environment, there are no bacteria around, so that when you fill in, there is no contamination, cross contamination could potentially happen. So, I mentioned such tanks. This is just an example of some of the high capacity such tanks you can able to use, and so it's in fact, I think you can probably, for example, I'm talking US example here, Brazil, which is kind of close to the Americas there, you can get lot of orange juice and maybe millions of gallons of orange juice processed, filled in maybe $1 million type tanks, and then you put them in a ship, and then you bring them back to somewhere in the US. So, for example, Florida, where you have a aseptic packaging line, you can able to package them in small consumer type package. So, this kind of brings some flexibility for processing and then packaging at a different time intervals. Now, this process is aseptic, so that means it is more self stable. So, you do not need to worry about product being spoiled as long as you maintain the sterility of this tank during processing. So, this is Professor Nelson. He was a professor in Purdue. So, he was the one championed aseptic processing over the years. Just want to acknowledge his contributions. So, aseptic packaging, basically this also gives much more flexibility. You can have consumer size package. So, for example, couple of fluid ounce packages as long as, or maybe as high as 8 million gallons of aseptic tank. So, you can have a wide range of packages are possible. Now, lot of the restaurants may be buying soups and other processed product, and they don't want a consumer size package. So, for that oftentimes you can use like what they call bag in a box. So, you may have a 55 gallon drum filled with your juice or soup, whatever it is, and then it is delivered to the restaurant, where the restaurant going to take a small portions at a time, but they consume lot of soup or products over the time. So, they can able to empty it much quicker, whereas in the home you probably not going to use it that much over time. So, that is where the consumer size packages are kind of come in. And this just some examples of the different products aseptically processed, and this is just to give you some of the different packaging equipments available, like including bag in a box, cups, pouches, and bulk storage, and so on. So, the aseptic processing brings much more flexibility to processor, so they can able to process in different scales. Now, coming to the food safety validation, you have to be much more complex in this case. So, when if from your lectures on food safety kinetics and food quality kinetics, we know the D value provides the decimal reduction time, and then the Z value is the temperature sensitivity of the bacteria. From knowing D value and Z value, you can calculate what they call F value. Now, that is very straightforward to calculate for the case of canning. In the case of aseptic, it is much more complex. So, this is where we have to use a mathematical modeling tool. So, first you need to know the D and Z value of your bacteria under the appropriate conditions. So, if you are processing at 140 C, you need to know what my D and Z at 140 C. Then you need to know the residence time distribution. So, in other words, within my whole tube, how much time it is going to distribute. So, give an example. Let us go back here. Suppose I introduce 100 particles with the liquid in the whole tube, and I count at the end of the whole tube here. Is all the 100 particles going to come in the same time? It is not going to come. So, some may be heavier, some may be lighter. So, there is going to be a pattern over time which is going to collect. So, this we call that as the residence time distribution. So, for this we have to collect that residence time distribution in the case of aseptic processing calculation. We also need to know the heat transfer. So, what is the heat transfer happening from the heating medium to the liquid? What is the heat transfer taking from the liquid to your solid? Maybe you have some carrots, you have some potato or other meat products in your soup. So, what type of heat transfer taking place? Then use a mathematical model to kind of look at the estimated thermal processing time, and you also try to look at the damage to the quality, like what is the destruction of nutrients or texture, all those things. So, you may kind of want to study the quality degradation kinetics. Then you kind of establish the thermal process time. So, with all the mathematical model, so you have a soup product, and then it says you have to process 20 seconds at 140 C. So, this is given this information by a model, but US Food and Drug Administration do not accept the model as it is. They want a biological validation. So, you have to take an indicator microorganism, and then you perform this process under those conditions, and then demonstrate that you achieve desired log reduction under those conditions. So, let us say you achieve 8 log reduction during certain process conditions, then you have to kind of demonstrate whether or not you can able to achieve that desired log reduction using the biological indicator organisms. So, the thermal process conditions, first you need to look at the residence time, model lethality, and then we modeled it with the inoculate pack study, and then you have to use the statistical confidence level for fastest 1% particle. What that means is, when you are doing processing, which one of the particle is going to be appropriate particle for doing your microbial safety check. In your soup, you may have potato, you may have carrot, or number of different products. Each may have different heat transfer characteristics. So, you need to find which one of the particle going to move the fastest. So, in other words, if your potato is going to move fastest, you choose that. On the other hand, if your meat has a lighter weight and move faster, then you have to choose the meat. So, whatever move faster, you have to choose. Why the significance of moving fastest in the holding tube? Because when a particle moving fastest in the holding tube, it's spending the least amount of time in my whole tube. Remember, the holding tube is the place where I am demonstrating the safety. So, that means if I spend less time in the whole tube, you may have a microbe in that particle that can contaminate the entire batch. So, you want to make sure that that particle is inactivated with free from pathogens and so on and so forth. So, that is where they are kind of able to look at the fastest moving particle with certain characteristics. So, here we are getting into a little bit food engineering or chemical engineering concept, the residence time distribution. Basically, the concept is I mentioned here, you say inject 100 particles, you are passing through a holding tube, and then you are going to measure how many particles you are going to come through. Ideally, if all the particles they may come in the same time, this is almost not practical. This is more practical. So, initially you may certain particles going to come through, and then certain particles may take even longer. So, from a processing point of view, these particles are much more difficult to they receive adequate treatment, whereas I am concerned about this particle here, because this particle is spending less amount of time in my holding tube. So, I want to make sure that my processing is done properly, so that this particle is properly treated. And then I have to do this under normal process condition. So, in other words, if the industry is going to do at 5 gallons per minute, then these experiments needs to be performed at 5 gallons per minute. You do not want to do it in a lab with 10 ml per minute and then try to scale it up to industrial conditions. Then once you have that, you also need to know the whole tube length. The whole tube length is basically what is the minimum processing time you need, and then what is the velocity at which it is flowing through the holding tube. Now, here we also need to know the fluid characteristics. So, if you look at milk, water, honey, and some of these products, these are called Newtonian fluids. So, what that means is, if you plot a shear stress versus shear rate, you are going to have a straight line. On the other hand, lot of the starches, lot of the protein and other type of products, these are shear thickening or shear thinning. So, that means with increasing processing time, they reduce the shear stress, or they may get shear thickening. So, for example, if you have certain what I call starches, it comes much thicker with increasing processing. So, it becomes a shear thickening. So, for that I think you use certain mathematical model, which I am not going to go into details, but just to take here, you kind of have certain velocity. You identify the maximum velocity based on 2 times the average velocity for Newtonian fluid, or for non-Newtonian fluid use this type of relationship. So, this lot of math goes behind here. For the purpose of this class, I think I am going to skip all the details, but if you are interested, there is a lot of books available where you can get into the details. The residence time also affected by the size, shape, density, heat exchangers and so on. So, you have to consider some of those things. And other thing you need to also consider is the Reynolds number. So, when you are processing fluid, the Reynolds number kind of indicates what is the characteristics of the fluid or the flow, and that is measured by this equation. Rho is the density, v is the velocity, d is the diameter, mu is the viscosity, and then you can able to see whether the flow can be laminar. When it is a laminar, it is going to have this characteristic parabolic curve, whereas it is dilatant, it may have different characteristics. So, you kind of needs to do some of those calculations as well. Again, from a velocity, you calculate volumetric flow rate divided by area, and you also need to look at some of these Reynolds numbers and other calculations. Once you have these things, once you know your volumetric rate, you calculate the average velocity. From the average velocity, you find out what is the maximum velocity. It is 2 times the average velocity, and then from there you also calculate your processing time, which is the knowing your d and z values, and from here you can able to calculate the holding tube length is the maximum velocity, which comes from here, and then ft which comes from here. So, this is kind of what you do. So, at the heart of the safety of your aseptic processing is sizing the holding tube. So, based on your product characteristics and the microbiological safety criteria, you kind of size the whole tube appropriate, then demonstrate to the FDA that you have delivered the appropriate processes. I know, like, I think I am going through a lot of new information for some of you. If you have questions, you can ask at the end of the discussion. Then you also need to know the modeling. So, for mathematical modeling, those of you with the engineering background probably familiar with the Fourier heat transfer equations. Again, depending on the sophistication, it can be 1-dimensional or 3-dimensional, but it kind of consider the heat transfer input to the liquid and the solid, and then how the temperature distribution within the solids and so on, and then they utilize different properties, and then you come to the biological validation. The mathematical model help the processor to see what if scenario. So, what if I had 5 gallons per minute, how do I process my samples? What if I increase the temperature from maybe 230 Celsius to 240 Celsius, how do I product characteristics look like? So, there are a lot of those what if scenarios can happen, whereas when you are submitting FDA for filing to show you are have a safe product, they expect biological validation. So, in other words, they expect actual microorganism to demonstrate the safety, and then it has to be something relevant. So, commonly Clostridium sporogenes is often used because that is very similar characteristics as Clostridium botulinum, and it also have a known D and Z values, and then it can grow and spoil or cause outbreak in the product. Now, aseptic processing is a continuous processing method, but still it is thermal process. So, your temperature and time is the principal critical process parameter. So, in other words, to demonstrate the safety, you need to have certain time at certain temperature. So, that is the principle behind it, but you also have the heating device, whether you are using tubular heat exchanger, your scrape surface heat exchanger, or using OMI heater, all those things can alter some of those results. Now, in terms of texture and viscosity, aseptic processing had a minimal impact on viscosity. The texture comes out a little bit softer than fresh, but much better than the canned product, and there may be toughening of meat at higher temperatures, and but generally the meat purees are not substantially affected by aseptic processing. And flavor, the product is much flavorful, and you, for example, in juices, milk, vegetable soups, things like that, you retain the natural flavor and you have a less nutrition loss. Remember, you are doing high temperature short time, so that means it's going to better retain the nutrient, and then you're going to also have most of the vitamins and other things are remain unaffected. So this is just some reference material. So I think so this book probably one of the very recent book which has a lot of information, and this is guidelines from FDA. So you can probably, if you want to learn more about it, you can kind of read some of the materials. Now we can stop and ask any questions. Yes.
Sir, good morning. What are the critical parameters monitored during a retorting cycle?
Critical process parameter monitored during retorting cycle?
Yes, sir.
Time and temperature.
Time and temperature. And what if any cold spot is means in that sum of the batch, if any cold spot remains?
So basically you are monitoring time and temperature at the cold spot. So for example, if you are processing spam, it's a conduction heated product, you are monitoring at the geometric center of the can the time and temperature, so make sure that it reaches the sufficient temperature under those conditions.
Okay, sir. Thank you.
Yes. Time and temperature are the in the case of aseptic, yes, it's also the critical control. Right. So how do you monitor? I think it's different. So in the case of canning, you're going to take the product, actual product, and then put the thermocouples and measure it. Whereas in the case of aseptic, the liquid and solid are flowing. So you cannot put a thermocouple and chase the thermocouple in the holding tube. So you basically put thermocouples at the entrance exit in the whole tube, but you look at predict the temperature distribution within the liquid and solid using mathematical models. So it's kind of little, instead of physical measurements, use the mathematics to predict your temperature values. Sure. Yeah. Okay. Okay, so the next one we are going to talk about is the ohmic heating. So ohmic heating is a technology which kind of had parallel development to aseptic processing. So even in early 1900s, the concept of ohmic heating was kind of tested, but I think never been commercialized until later in 1980s when ohmic heating kind of commercialized. So if you look at the history of a lot of the food processing technologies, the concepts may be known a very long time, but it takes longer time to commercially adapt the technology. Number one, there's a lot of science needs to be studied, understand. The second, food industry tend to be very conservative, so they probably have hesitation to adapt new methods until they realize it's the right thing, and then it becomes once one person step in, adapt, then there's going to be a lot more people going to follow and adapt the technology. So most of you probably use a water heater at home. So you take a heater, electrical resistance heater, put a piece of bucket with the water, and then you are heating the water with the heater. So the same concept is applicable in the case of ohmic heating. So essentially you have two electrodes, and you're going to have a food in between, and then you are applying certain voltage. Then the current is passing through the food. The food acts as a resistor, thereby you can able to heat rapidly the food. And here the electrical energy applied is converted into heat energy, and then it also volumetrically heating their mass of the product. So if you remember, we talked about conduction heat transfer, where the heat transfer happening out, and then this center is going to heat later. Whereas in the case of ohmic heating, the entire mass is going to be heated when you pass the electricity. So that's called volumetric heating. If you look at microwave, it also have a similar volumetric heating. Now, the property that allow the material to heat is called electrical conductivity. So by adjusting the electrical conductivity of the liquid and solid, you can make the liquid heat faster or solid heat faster. So you can be able to adjust different things. And so you have, with proper formulations, you probably don't have issues with a non-uniform heating. A lot of times when you want to ensure the food safety, you need to understand the microbiological concept, but from a processing point of view, you also make sure that you are delivering your energy much more uniformly and consistently, and I think ohmic heating can help to accomplish that. So the concept of ohmic heating started around 1841 with Prescott Joule, and even in the early days of milk pasteurization, they were attempting to pasteurize milk with the ohmic heating. However, if you look at the literature, a lot of those data in the early 1900s disappeared from the science later, because you had World War I, World War II. So I think the focus on some of the new developments kind of moved away, and people just stayed with the canning and traditional methods. So the innovations kind of didn't happen. Then it took 1980, a UK based company called AVP Baker Company. They reintroduced the concept of ohmic heating, and today in Europe and many other places, the ohmic heating concept is kind of adapted. So basically, the Joule's law governs the how ohmic heating happens, and I mentioned the electrical conductivity is the property of the material where it conducts the electricity. So the heat generated within the product is given by Q, is given by I square, R, and time. Q is the energy produced in the product, I is your current passing through your product, R is the resistance of your product, and then T is how much time processing time. So, you can able to rapidly heat the product, like for example, you can increase the temperature 1 Celsius per second and so on. So, it is quite rapidly you can able to do that. So, the energy delivered can also related to traditionally mCp delta T. When you do a conventional pasteurization or sterilization, the energy delivered can be used mass times specific heat by time, whereas here you can use a different approach. And this slide just to show you kind of illustrate how the current, voltage and the resistance kind of relate to part of the Ohm heating process. The current is trying to flow through this small restriction, and the volt is the driving force which drives the thing, whereas the resistance of the material trying to block the passage of current. So, that kind of provides an idea how the Ohm heating functions. The temperature increase during Ohm heating can be measured by V square, and then you have what they call product conductivity rho, and then you have area of cross section, and then distance from the electrode, the mass, and then Cp is your specific heat. So, this is kind of tells you how much temperature increase happens during Ohm heating. So, during a traditional Ohm heating, you are going to have multiple Ohm heaters. So, you may have in this example 1, 2, 3, 4 Ohm heater. So, if you look at the rest of the thing, you have a feed pump, you have a holding tube, cooling section, a septic tank, filler. You may remember you have seen all these things with the aseptic processing. Only thing different here is you are using a Ohm heater instead of conventional tubular heater or scrape surface heat exchanger. So, the concept of aseptic processing is adapted here, just you are replacing the ohmic with the Ohm heater with the traditional heaters. So, why do I have so many different heaters? So, I mentioned the property of the food material which conduct the electricity is the electrical conductivity. So, what happens is when you have a food material at the initial temperature, room temperature 25 degrees Celsius, you have certain electrical conductivity value. Then you are passing electric current through it. So, it is going to warm up that material. So, increase the temperature say 50 Celsius. At 50 Celsius, the electrical conductivity value may be increased, maybe from 1.2 it may become 2. With that, it allows more passage of electricity, then you can probably increase the temperature much more rapidly. So, you go to this stage 3, and then you are going to increase the temperature further. At that higher temperature, say 75 Celsius, the electrical conductivity become higher. So, that means it is going to increase. So, that means the electrical conductivity value and the temperature, they are coupled with each other. So, the temperature increase the electrical conductivity value, it pass more current, that means it is going to increase the temperature and so on. So, this is the reason why they kind of have a controlled temperature increase. They probably have 4 heaters, so that they can modulate the temperature increase in a controlled manner. So, that maybe from here the heater 1 it may be going from 25 to 70, 70 to 90, 90 to 130, 130 to 160, 150. So, you can have a controlled temperature increase rather than what they call runaway current. So, you can suddenly rapidly increasing the temperature. So, this is just a pictures illustrating how a Ohm heater may look like. it may look like a pasteurization equipment, but essentially you have a lot of different heaters, holding tubes and cooling heat exchangers, and then you have storage tank and so on. So, this is kind of when you do canning, you have temperature, your heating medium, the conventional product going to slowly increase the temperature like this. Whereas, with the Omi heating, you can see that the temperature increase is slow, but as you increase the temperature, you are going to increase the electrical conductivity, then you are going to rapidly increase the heating rate, further increase the heating rate, then it just quickly rise the temperature. So, this is going to much rapidly increase the temperature, and it does not, in the case of conventional, you are going to have conduction, convection, heat transfer. So, that means the heat has to travel from out to in, it is a slow process. Whereas, in the case of ohmic, the whole volume is going to be heated. So, that means the heating is going to be much more uniform under those conditions and so on. Now, what type of electrodes people use? There are different electrodes can be used. The electrodes may be made of graphite, aluminum, stainless steel. Now, when you use different metal electrodes, you can potentially have what they call electrolysis. So, that can be potentially introduce some undesirable compounds. So, what they do is they coat the electrode, platinum electrodes with the platinum, so that you can stay inert. So, you only pass the electricity, it does not interact with the product. Otherwise, what may happen is you may pit the electrode. So, in other words, with passage of electric current with so many uses, some of the aluminum or metal particles can migrate into food, and again, which is also not desirable, because from a regulatory point of view, you have to maintain the food products free from any foreign objects, things like that. So, that is where you have to coat with the platinum electrode. And you can able to develop methods to measure how much electrode migrate into the food, so that you have to report that part of your filing process. The electrodes can be different sizes, like they can be collinear, or the electrodes can be staggered like here, or they can have parallel plates, or you can have a parallel rods. So, different configurations are possible. The passage of heater, the heat exchanger can be coaxial profile. So, what that means is you have a tube, and then you are passing through the material here, and then you have an electrode here, so that you are going to have one field here, one field here. So, you can able to have current passing through them. So, this is suited for product with the low electrical conductivity, it carries the larger current. You can have aligned field electrodes. So, you have two electrodes, and then the product is moving here, and this is suited for product with high electrical conductivity. So, in other words, if you look at Omi heating, the design of choice of your electrode depends on what type of product you may be processing. If you look at traditional aseptic or canning, some of the design considerations does not limit what type of products you can process. You can product wide range of products, whereas here you may have to think through, okay, I am going to process fruits with certain electrical conductivity value. So, that means the electrodes I am going to use needs to be this design, and so on. So, there is some consideration you have to change, and then if you significantly change that electrical conductivity value, different formulation, you may have to look at different set of electrode designs. This one also just to illustrate how the voltage gradient is influenced by the voltage and the distance between the electrodes. So, you have the product here, and then two electrodes, and it has a certain gap and then certain voltage. you can change the voltage gradient by increasing the voltage. So, maybe let us say this is 30 volt, you increase here 50 volt, and then this distance is 3 centimeters, you keep the 3 centimeter, but the ratio is different. So, you can have higher voltage gradient, or you keep the same voltage 30, and instead of distance 3, you may increase the distance, you decrease the distance to say 1.5, then also you can change the voltage gradient. So, there are a number of ways you can change these properties. The other thing you can do is you can alter the electrical conductivity of your material. By altering the electrical conductivity, also you can able to change your properties, so that you can able to get the appropriate heating rate. So, in all these cases, you are kind of trying to have certain voltage gradient in the ohm heater, so that you achieve certain heating rates. So, you can do that by adjusting the gap, or increasing the voltage, or change the properties of the your formulation. So, one limitation is how do you change the electrical conductivity of food formulation? Give you some thoughts. So, the answer is you can change that by adding or removing salt. So, salt can increase or decrease the electrical conductivity of your food material. So, you can able to do that. What that means is only so much salt you can add to your food material. So, you cannot add large amount of salt to increase the electrical conductivity, because people need to consume the food. So, if you have too much salt, that is not considered healthy, people may not perceive that as a healthy option, and so on. So, there are constraints placed to that as well. There are different companies supply ohm heaters. These are just to give some examples. Some of them are located in the UK, France, and then Japan, Italy, and so on and so forth. So, we already kind of talked about electrical conductivity, and we will now look at the factors affecting electrical conductivity. The electrical conductivity of the material is going to be affected by what type of salt ions you use, and what type of dissociation they have, what type of viscosity the medium you have, and how quickly the temperature increasing, cellular structures, and all those factors can affect the electrical conductivity values. The next one, we are borrowing some literature from the electrical engineering field, because now ohm heating is a electrical based technology. So, that means you need to have some knowledge of electrical engineering, and the reason for this is just to show how the product going to heat inside the ohm heater. That depends on how the product align itself within the heating medium, or they align as a resistance in series. So, that means all the particles move through in a circular row. So, there may be heat is kind of coming in, heat first, second this, third, and so on, or are they going to arrange in parallel. So, there may be particles flowing in 2 rows in ideal case, but in nature you may have random configurations. So, that means some particles may be flowing in series, some flowing in parallel, and so on. So, this is something you have to kind of make estimation. Different food materials have different electrical conductivity values. So, carat, for example, 0.041 Simon per meter. Simon is the unit for measuring the electrical conductivity. So, it kind of provides that value. Whereas, if you look at salt solution with 0.2% salt, 0.34, when I add 2% salt, it significantly increases the electrical conductivity value. So, again you can alter the electrical conductivity, you can by adding or removing salt. The other factors affecting the electrical conductivity of the material is the fouling. Remember, fouling is when you process a protein product, like for example egg yolk or milk or any protein products you are heating, you are going to have deposits in the heat exchanger surfaces. That's the fouling, and that needs to be removed. If you don't remove, it's going to reduce the heat transfer to heat exchanger surface. The same way, when you have Ohm heater, you're going to have heating electrical resistance heater here. With usage, you're going to start forming fouling, and that's going to decrease the efficiency of your electrical resistant heating. That means it's not going to pass the electricity properly, so you have to kind of again pay attention to that. The frequency of power source probably also pay attention. So the line frequency in the US is 50 or 60 hertz. So can the frequency increase to 100 hertz or 120 hertz? Those also affect the electrical conductivity values. So this slide just to illustrate what happens when you are heating potato with Ohm heating, or like in this case starch with Ohm heating. So you start at 25 degrees Celsius or 20 Celsius, you have certain low value here, and then as you warm, you can see that the conductivity increases from say 0.05 to say 0.1. Then it is relatively stable from 40 to 70 Celsius. And at around 70 Celsius, you are going to gelatinize the starch, say in a potato. Then you can see that it breaks down. So then it's going to significantly increase your electrical value, say from 0.1 increases to 0.3 or 0.4. That means the heating rate may be slow here. Once the electrical conductivity starts increasing significantly, the heating rate also significantly increase much more faster. Here we kind of illustrates that you have a potato particle and how the potato is oriented with respect to the electrode. So you have electrode here, the particle here, and then the heating rates can be so the liquid is dotted line. So this is the liquid, whereas the potato is here, this is the solid. So this is when the field and then kind of parallel to that, whereas here electric field and then the potato is, and you can see that the same condition, but you just change the orientation, the heating rates of solids and liquid reverse under these conditions. So again, Ohm heating is kind of much more complex compared to some of the traditional canning and other methods. So that's where again you need to have mathematical modeling to understand various things happening during Ohm heating. This slide just to show the electrical conductivity of solids, like for pieces like a potato, how when you change the applied voltage from 0, there is no current passing through, to 40 volt per centimeter, like so much volt gradient is there, and you can is able to achieve under those conditions. This is showing for a liquid. So for example, orange juice, and again at the different voltage gradients what happens. So generally, as you increase the temperature from 20 to 80 Celsius, you can see that straightforward increase. Then it's kind of dropping here, but this is more experimental artifact, because at 100 Celsius water start boiling, If you don't pressurize it, then you're going to evaporate. So that's going to give you a different sense, false temperatures reading. So this is where this data is not reliable. So you have to have a pressurized electrode or system to measure the electrical conductivity at higher temperatures. So in terms of critical process temperature conditions, temperature and time. So what is critical process temperature and time means? So that's a minimum temperature and minimum time your product needs to receive during processing. And in the case of overheating, again it's the temperature and time as the critical process parameter. Overheating is also a complex process, so you can able to model that using multiple field. So you have an electrical field. During that, you are going to generate certain voltage, so that's your heat generation. Then you have a temperature distribution field here, and from that, I think the details of the models are available in the link shown here. And rather than going into details, I am going to just highlight two results. Let's think about a simple case. You have maybe a 1 feet long small bench scale OMI heater. So you have OMI heater and electrode, and let's say this is 1 feet diameter, 1 feet in length and maybe 1 inch in diameter. And I put some type of solid in here, and then I am going to fill the rest with the some heating medium, so water or certain salt solution. What I am interested in the modeling is, I am interested to see how the temperature happens within the solid and within the liquid. So in the first case, you are processing 150 seconds, you are single cylinder particle is 1/3 as conductive as the fluid. So the fluid is more conductive, so that conducts electric current faster. The solid conducts electric current slow, and you have electrode here, electrode here. So what happens is, if the solids conduct slow, it's going to be heating slow, showing maybe more green color, showing its less temperature. Whereas this is much hotter, so showing somewhere 115, 116. So in other words, the current try to flow wherever the electricity allow that to pass. Since the liquid in this case has a higher conductivity, the current try to pass through without passing much in the solid. In the second case, so the first case is a well mixed fluid, so that means you have much more uniform conditions. In the second case, you have static fluid. So that means you can see here the solids kind of slowly heating, but you are not mixing the fluid. So that means you are going to have a lot of hot zones in the top, because there is a lot of electric current passing through, whereas here you have less current is passing through. You kind of look at those two scenarios, whereas this is a mixed. So you can think about, you place the OMI heater in a table, or you put a OMI heater in an agitating table. When you put an agitating table, the fluid is well mixed, so you have much more uniform temperature, showing the same color, so it's around 116. Whereas in this case, when you have no agitation, you're going to have more heating in the sections where current can easily pass through. So that's why it's much harder compared to some section where you have cold spot and so on. So the point here is, in the OMI heater, if you have change in electrical conductivity between the liquid and solid, you could have different heating happen in the liquid and solid, and then you're going to have non-uniform temperature distribution. When you have non-uniform temperature distribution, that means that you are not going to heat the entire mass same originally we thought possible. That means you are going to potentially have microbes there. It's probably going to potentially food safety problem. So, in other words, you have to understand how well the electrical conductivity in the liquid and solid mixed uniformly, so that for the current it looks the same mass, whether it is a liquid or solid. If it is the same electrical conductivity, it is going to heat much more uniformly, whereas when the values different, then they are going to have different temperature distribution. So, the second case is you have single particle. Here this is more conductive, this is less conductive, and then it is well mixed. So, again you can see that it is a much more uniform temperature. Since the product is much more conductive, you can see that product is much hotter compared to the liquid. Whereas, in the case of static system, still product is hotter, but you are going to have cold spot because much lower temperature in this vicinity where there is not much mixing is happening and so on. So, again when you look at some of these advanced processing technologies, you have to look at where is the uniformity of my treatment. If I do not have uniform treatment, where is the location of the least treatment, and then try to understand that. Then you characterize your microbial kill under those conditions, so that you can have estimate to the regulators. So, the principal mechanism for microbial kill with the warm heating is primarily heat, and there is no contribution from the electrical heat. So, in other words, I am heating with the warm heating, but I am going to assume I am using only 140 C. There is no contribution of electrical field. Whereas, I think more recently researchers trying to include some of the frequency effects and other electrofield effects, see whether there are non-thermal effects of electric field in terms of killing the bacteria. But right now, from a regulatory point of view, you primarily look at only thermal effect during warm heating. So, warm heating can be processed for number of different type of products like soups, liquid egg, juices, seafood. It can be used for extraction, fermentation. So, interestingly, when you apply electric field under certain conditions, it is going to stimulate the growth of microorganism. So, you can accelerate the fermentation process with warm heating. You can also use warm heating as a branching step, and there are commercial applications like fruits, sliced fruit, sumi products and so on in the market. So, this is just some of the reading material you may find useful for the purpose. With that, I am going to stop here for some questions.
So, this heating method, is it only suitable for liquid substances?
Warm heating?
Yes.
It
Means
can.
in the last slide, the examples which you gave, that stew and everything, those were liquid substances. So, can we use this method for solid products
You
also?
can use it for solids as well as liquids.
Okay.
But I think the idea here is you want to have homogeneous electrical conductivity values. So, when you have liquid and solids, you may have different liquids have a different electrical conductivity value, and solids may have different electrical conductivity value. Controlling them may be a little more challenging. Whereas, if you imagine you have fruit puree, you have much more homogeneous, same electrical conductivity value, you can able to accomplish.
Yes, so that question also I wrote, that how is this uniform heating ensured in a ohmic heater in case of heterogeneous food like soup with fluid?
When you have a heterogeneous fluid, it's much
Yes.
more difficult to demonstrate the heat, the ohmic heating. So then you have to look at the electrical conductivity product characteristics, and then you have to find the different resistant characteristics, and then relate back to the time and temperature, and then you have to identify the cold spot, all those things. So the calculations going to be much more complex. It can be done, but it's much more complex.
Okay. Okay, sir.
So ideally, you want to have much more homogeneous electrical conductivity value, so that the current can pass through much more uniformly.
So, sir, is there any alternative for this heterogeneous kind of things?
So think about we are going to learn different technologies during this advanced processing type of lectures,
Yes.
and each one is a tool. So each has certain benefits, each has some limitations.
Yes.
So that means everything is not going to be uniformly applicable for all the scenarios. So you have to use different tools wherever it's useful.
Okay, sir. Thank you, sir.
My question is, what kind of products undergo ohmic heating and what kind of products undergo aseptic heating? How is that decided?
Right, sure. So again, as I mentioned, aseptic processing, ohmic heating, these are all two different tools. Both prepared to accomplish the same thing, which is sterilization of the product. Aseptic processing is relatively more conventional thermoprocessing type method, whereas ohmic heating require knowledge of electrical conductivity, all those things. Ohmic heating probably much more useful when you have very, like, for example, you think about dense fruit puree or dense liquid type of material. Pumping through a aseptic processing system, it may be challenging because it has a high viscosity, all those things, and then the heat transfer may be a little bit slow. Whereas ohmic heating doesn't care because it doesn't worry about conduction heat transfer, it worry about the electrical conductivity. So as long as that material has the same electrical conductivity, it will heat quickly. So under those conditions, electrical conductivity probably going to work better, or that product ohmic heating maybe work better. Whereas you have a simple liquid or liquid with solids, aseptic processing may be good under those conditions.
Right, or is it probably the kind of shelf life that they expect of the food product?
No, the shelf life, both, if you properly design, they are going to have a long shelf life similar to whether it's aseptic or ohmic. They are same tools. You know, like if you think about in the kitchen, there may be multiple knives there, but you are not going to use same knife for all the things you want. Maybe different jobs require different knives. The same way, different product categories may require different type of technologies. So in the case of ohmic heating, it works well when you have high viscous product or highly concentrated type product, whereas aseptic may be more liquid with solids or more liquid type products.
Okay, sure. Thank you.
Hello, sir. So my first question is, as we know that many of the industries are working on the conventional heaters, so would it be justifiable to switch on the ohmic heating if they want to switch? Because as we know that process involved, there are many insulated materials we want for the ohmic heating. So, sir, is there chance that the companies would hesitate with the cost in it?
Right. So again, to have different tools, right? Like ohmic heating, aseptic. Later on, we are going to talk about microwave heating. Each has a different principle of operation, different heat transfer mechanisms, and when food processors want to implement, they have to consider the cost, they have to consider the quality, all those things. So they have to choose based on that. So they don't have to use ohmic or microwave or aseptic. Remember, consumer, when they buy product, they are not buying a product, I am buying because it's ohmically heated, or I am buying because it's aseptically heated. They are buying because it's a better quality, taste better, all those things. So the technology is going to stay behind the scene. It's a processor. They are going to look at the economics, what facilities available, what are the things they have, and then they choose which direction they want to go.
Yes, sir. In that context, I want to add, just like, sir, we have seen that there are many government and regulatory bodies are trying to say that we want to reduce the dependence on the conventional heaters, because pollution is the main concern, or the method which we are using for the heating is main concern. So the government or any regulatory body is coming to us to help the industrialists to for these instances, so that cost would be lesser, or subsidize them on the when they are going to adopt these new technologies.
Right. So again, you are bringing the sustainability dimensions. So if you compare canning has much more emissions because of the heat loss and other things. Aseptic going to be less, whereas if you look at ohmic heating and other electro-based technologies, because they use electricity, the electricity can be produced using even solar heaters and so on. So there's going to be different dimensions. Now the food processor, they have to stay in the business to make money, to provide salaries for the people, they need to stay profitable. So they have to look at the big picture, is this being supported or it's not being supported, and then they make the decision. So in one country where some others have supported, they may be going for ohmic heating. In other country, maybe they may choose something different because that is not supported.
My second question is, are we in the position that we can comment on the effect of pH and other material properties such as size of material on the process?
For ohmic heating?
Yes, sir.
Yeah, it's going to be similar to thermoprocess. So acidic products going to have much shorter time, because because the spores, bacteria doesn't grow well in acidic environment, so they require only mild treatment. So it's kind of similar. What's the other one?
Sir, other one is the material properties such as size of material, if you are talking about the solution.
The size of the material, the diameter of the particle?
Yes, yes, sir.
So if you look at the ohmic heater, the particle size probably is relatively less important, because in traditional conduction, convection heating, the size is important because how much time it takes to go through the particles. Whereas ohmic, supposedly the whole thing going to be heating, so then the sizes become less important.
So my third and last question is, if we are talking about the electrical ohmic heating, sir, we know that if we are increasing the distance, there will be increase in the resistance also. Sir, so we can comment that it there not the chance that if you are using at industrial scale, so it may be the chance of over processed or under processed.
Yeah, you have to kind of remember in the one of the first slides I showed multiple electrodes. So you can able to control the heating rates in each section, so that you can see what temperature the product goes through different ohmic heater. And these can be computer controlled, so that means you may have thermocouples attached with your computer that monitor the process, and then it can able to regulate the passage of electricity to different ohmic heaters, so you can able to control your process efficiency.
Sir, out of curiosity, sir, as the question was arose that in the heterogeneous method, how we can control, sir, could we use the agitator with the process, so that the heterogeneity or the the problem with the heterogeneous material can be solved?
Yes, I think definitely you can add a agitator of some sort inside a Omi heater. Now remember, Omi heater itself has, you have a tubular structure and then you have electrodes, and then you are adding an agitator. It's going to add the mechanical complexity of your system. Now whenever you add multiple components, you need to make sure that all those components work in sync. So what if you have a system and the agitator stopped working during the process? Then your assumption may not be valid. So all those things you have to keep in considerations.
Okay, sir. Thank you, sir.
Good morning, sir. So, is there any particular compositions for the product which is used in ohmic heating?
Any particular composition?
Compositions of the products.
So the electricity doesn't care the composition. It's just to consider the electrical conductivity. So you may have salt, much higher electrical conductivity, whereas maybe starch or protein may have a different electrical conductivity and so on.
So, does nutrient content get affected by heating any particular product?
So again, Omi heating or aseptic processing, when you heat rapidly for a short time, the nutrient content is supposed to be preserved. When you have a prolonged heating, that's when you get nutrient damage.
Or sir, any particular storing chamber so as to reduce the reactions between the product and the chambers, storing chambers where we are storing the products?
So you're talking about the electrode and reaction?
Yes, sir.
So you know normally when they have electrodes, when you have for example stainless steel electrode at high temperature, you may have electrolysis. So that's where they may be coating with the platinum coated electrodes, so that it reduce the interaction between the product and the electrode. So it doesn't happen.
Okay, sir. Thank you, sir.
So sir, my question is, in case of like ohmic heating or other non-thermal technology, we increase the temperature, shorter exposure duration we mostly prefer. In case of ohmic heating, pulse electric field as well as CP. So due to that, we observed that because of this sudden exposure, the proteins or starch molecule, in case of proteins, the active binding site may be explode, or in case of starch, it will be like amylose pectin chain length distribution will be defected. As a result, in final component, what we get, whatever the exposed site of the protein and starch, it will bind together. As a result, it can reduce the bioaccessibility of the nutrients when you consume the human food. So how to overcome it?
Okay, can you kind of?
Okay. So sir, when we go for the short time treatment, because of that, in certain case protein they expose the hidden binding site for the external parameter. As a result, it can improve the digestibility. In case of starch also, it can depolymerize at a minor scale. But in a negative consequences, if we slightly over process, for example more than 5 seconds, as a result the newly exposed active binding site of the proteins and the depolymerase start will be bind together. In fact, when you consume that, whatever the bioaccessibility the human body should absorb their body, it practically reduce. So how to overcome this? Because
right, sure.
In many processed food item we found the similar consequences.
Right, sure. So this is a very good question. Now, if you look at the research overall done, especially in the US, a lot of the effort primarily focused on food safety. You want to demonstrate the safety, microbiological safety of the processes, whether it's Omi heating or high pressure, pulse electric, all those things. The health side of how those processed food affect the health and wellness, I think that studies are only beginning to happen. So yesterday morning there was a discussion about the gut microflora and processed food. Those are things probably we don't have yet. So it's probably going to be the next 10, 20 years, some of those studies needs to happen. Then we will probably have a better insight which one of these technologies better health benefit to the other technologies.
in the industry, when they are doing pasteurization, what is the heating technique that they are using? Is it ohmic heating itself?
What is the heating technique they use in the pasteurization? So, normally, at least with the US perspective, they use traditional pasteurization, for example, milk and other things. They use the traditional pasteurization. Now, more recently, in the last 10-20 years, high pressure pasteurization becoming more common, and it's kind of gaining more attention.
Sure, but what is the heating process that is involved? Is it is it the electrodes that are used, or is it the steam? How is
so,
that?
in the case of pasteurization for milk, that is more they use plate heat exchangers. So, essentially you take steam and then you heat the milk, your plates, and then the transfer the heat to the milk, and that's heat the milk. So, it is essentially like steam or hot water.
Okay, okay. So there are two types of milk products. One that can even after pasteurization has to be refrigerated, and there is another carton which can sit outside at room temperature.
Right.
So what is the difference in the processing of those two? One is aseptic, the other one is the regular pasteurization, right?
Right. So, remember we talked about the term pasteurization, commercial sterilization. The same concept is applied for milk as well. If you do pasteurization, that means you are inactivating only vegetative bacteria, spores are not inactivated, you keep them in the refrigeration. When you heat the same milk to 140 C instead of 72 C, you are going to expose much higher temperature. Then it is called UHT pasteurization, ultra high temperature pasteurization. The milk becomes self stable, and that can be kept in the room temperature.
So why isn't the dairy industry adopting ultra high temperature pasteurization?
So, again, this is one of the things going to be, the answer is different for different countries. UHT processing is probably more common, I think, in India and in Europe, where the refrigeration handling network, all those things is relatively either small or non-existing. So, it is much easier to store the milk in a Tetra Pak container in the room, and then you open it, then you consume it immediately. Whereas, if you look at the US, you have extensive network of refrigeration. Most of the homes have refrigerators. So, that means the consumers, they are primarily interested in preferring the pasteurized milk, but they do not like the burnt flavor of your UHT milk, because like I think they acquire taste, that burnt taste, whereas that does not bother the consumers in India or some other places. It is just how they are kind of accustomed to that. So, in fact, I think there were studies done where they were trying to bring UHT milk and feeding young children the UHT milk, so that when they grow up drinking UHT milk, they acquire the taste, so that they become adapters of UHT milk. So, those type of things, but nevertheless today pasteurization is the predominant technology in the US milk pasteurization industry.
Sure, thank you so much.
So, sir, my last question is, in case of like ohmic heating, the fluid will be go in case when you go for the simulation, it will be go for the pipe flow. In certain case, we know that the in the middle of the section the velocity will be high, and the edge of the pipe their velocity will be less. As a result, the microbes will be deactivated due to this certain shock of the electrical field and conductivity of protein denaturation. So, during this entire process, so I read several things that in case of that there is a safety concern, because whatever the instrument we are using, there is a wear and tear in case of when we are going to use the electrical rod where the electrical currents will be passages. So, we already established certain rules already forcefully applied to the instrument. So, is there any kind of practical application or regulatory body is there to check either this condition is fully maintained or not?
So, again it probably depends on country to country. So, in the US OMI heating is not at the moment very broadly commercially used, but they normally check the what they call the electrode from an Food and Drug Administration. Their primary goal is to see what type of things you are adding or removing in the food. So, that is why they are worried about this. Whereas, if you look at the wire connections, electrical connections, all those things, it may be maybe for example, there are government agencies which deals with the worker safety, all those things, they may be kind of follow up on those type of issues.
Okay. Sir, in case of like if you want to formulate the like heat transfer rate or mass transfer flow, mostly we are using as of now, we mostly use the COMSOL software that is too complex. Is there any simple software that can be industrial scale or optimize model fitting software is still exist that we can use, because of that we can collect the data, simply fit the data, we will get the temperature profile distribution?
Yeah, again unfortunately, you know, some of those flow field, electric field, coupling and distribution, all those things, it is a complex. You know, there are COMSOL is one example, you have Fluent, there are finite element softwares and other things available, but someone needs to learn and kind of practice them. And I think other thing is probably if you make them too simple for the end user, people may probably make mistakes by not following some of the physics concepts, and that can be potentially problematic too. Okay. So, at least I am not aware of any simpler software for some of these applications.
Okay, sir. Thank you. Okay, sir. We can end here, and we will come back at 11:15. Okay. So we go for this.
So, this presentation we are going to see microwave heating or microwave processing. So, in the case of OMI heating, we saw it is a volumetric heating, you know, the both the liquid and solid, if they have the same electrical conductivity, they can heat together rapidly and you can able to minimize the temperature distribution. Microwave heating also an electrical based technology, and you use a similar concept volumetric heating, except the mechanism of heating is probably going to be different. So, when you apply microwave, the food absorbs the microwave, and that increases the temperature of the food, and it is going to destroy the microorganism and preserve the food. So, basically it is a thermal processing, time and temperature as the primary thing. Now, the non-thermal effect of microwave, they are there, but they oftentimes they do not consider significant. If you look at microwave history, it is kind of very interesting. It is relatively younger technology compared to say OMIC or some of the other technologies. In around 1940s and 50s, there is a radar engineer by name Percy Spencer. He was kind of working on some defense related things, and he had a chocolate bar in his shirt, and kind of noticed when he went to the radar room, the chocolate became melted. He was curious what caused the melting, and then he realized that the exposure to the microwave melt the chocolate. Then he kind of conducted additional experiments, eventually led to the microwave. So, the early days of microwave ovens, even for the home use, they were big cabinets, maybe probably the size of that audio room in the back. So, they are very huge, and because all the electronics and other things there. But probably eventually in 50s and 60s, in the US at least, microwave become more common household items, and so it became everybody start using microwave. However, when you look at the industrial application of microwave, particularly for pasteurization and commercial sterilization in the US, it took almost around 2000 or 2015 when the first microwave petition was approved, or FDA issued no objection, so that it became a commercial process. Again, the Food and Drug Administration, they don't issue a letter of no objection, just you provide data. They want you to provide the scientific reasons why some technology work, and then if there is a process deviation, how they can take care of some of those issues, and so on and so forth. So, that is where it takes a longer time for the industry to adapt the technology. So, if you look at the microwave, it is a wave. So, that means it has a wavelength, it has a frequency, and then if you combine those things together, the lambda is the wavelength, and then f is the frequency, that is the speed of light. So, because microwave is essentially electromagnetic wave, speed of light is constant, is 3 into 10 power 8 meter per second. And the household microwave use certain frequency 2450 megahertz, and then 915 megahertz is what they use in the industrial microwave. Why 915, why not 2450? Because the lower frequency going to have higher penetration depth, because when the industrial environment, you may be processing samples maybe with multi layers, maybe a very thick sample, having a longer penetration of microwave enable to process food much easier than shorter penetration depth. Because at home you are not going to cook big stack of material, you are going to heat only small portions. So, having a small depth is probably it's okay. So, this is kind of part of the electromagnetic spectrum, and you can probably pay attention to this, because later on when we do the radiation, you will also use the same spectrum. If you look at one end of the spectrum, you have the X-ray, gamma rays, and so on. So, they kind of have certain properties, certain wavelength, and then certain frequency. The other end of the spectrum is your radio frequency wave and then microwave. You can see here the wavelength is 1 millimeter, 1 centimeter, 10 centimeter, and so on. So, as you increase here, the wavelength increases, but the frequency in this side is decreases. So, it kind of goes in the opposite directions. So, this is kind of where the microwave is used. Whereas, if you look at here, this is the visible spectrum. One end of the visible spectrum is your UV, the other end of the visible spectrum is your IR, infrared radiation, all those things. So, these are all kind of part of the same electromagnetic spectrum, which kind of used for the various food applications. And this just a slide just shows that what are the different frequencies adapted for microwave and OMI heating for various food processing applications. Now, what are the benefits of microwave processing? It is a volumetric. So, that means whether you have a small particle or a big particle, you can able to heat them together. You can reduce the processing time. Now, when you do heat transfer with heat exchanger, you are heating a product, the material is hot, and then when you, it's kind of difficult to turn off the heat immediately and bring the product to cool down. Whereas with the microwave, you can turn it on, it's heat. When you turn it off, there's no microwave delivered, so it's going to cut off that heating, so you can able to distribute that temperature much more. And then you can also allow them to deposit that microwave in a particular shape and size. It's much more energy efficient. It can be combined with energy sources and chemicals. Now, even though microwave has the promise of what they call volumetric heating, we will see later on there is going to be uneven heating. So, again, there are properties of the food material called dielectric properties, that different food substances have different dielectric properties that result in uneven heating. Again, understanding that will help you to prepare your microwavable food and frozen meals and so on and so forth. This is a simple concept to illustrate microwave processing. So, when you apply microwave, this is part of the electromagnetic spectrum. So, think about a simple torchlight. You take a torchlight on, shine on the surface, the light is going to apply it all over the surface. The same way, within the microwave, you have a magnetron which generates the microwave, and then you have a waveguide which transfer the wave into a chamber, and then it's going to distribute. And then you can have a chamber design in such a way that that wave is kind of reflected different ports and then focus on your sample. So, the sample is going to absorb microwave, and then how does microwave heat the food? The simple answer is most of the food substances have water, and water basically trying to follow the microwave. So, microwave I mentioned 915 megahertz or 2450 megahertz. So, it is like so much frequency, hertz is 1 over second. So, it is 10 power 6 per second. So, it is much more rapidly moving up and down. The water molecules try to follow that frequency, it also try to move up and down. When they move up and down, they collide with the adjacent molecules, and when they do that, that create a friction, and that result in temperature increase. So, that is how the microwave can create that. The same way, you also have salt like sodium chloride, for example, sodium and chloride ion. They are also similar to respond to the microwave, and then you can also get some heating happen during that microwave processing as well. So, from an industrial scale, like we said, home microwave have been there long time in the US, probably from 60s and 70s, and now all over the world many households have microwave at home. So, it is kind of people kind of mostly use them for preparing, heating meals and things like that. But the industrial application for microwave in the US is very slow to adapt, because there are non-uniformity in heating, and the scientists have difficulty in kind of able to demonstrate that. So, there has been some work done at Washington State University, where they adapted what they call microwave assisted thermal sterilization process. So, what it is imagine you have some soup or you have some material, and then you are going to package them in a polymeric pouch. So, that they are going to be sent through a certain mechanism. So, here you have a product is going to be heated to certain uniform temperature. So, maybe let us say you maintaining at 50 Celsius or 60 Celsius, you are going to maintain that, and then you are going to apply microwave in a particular zone. So, when you condition everything at the same uniform temperature, the electrical properties like the dielectric properties going to be in the same temperature. So, that means the temperature increase is going to be much more uniform, and then it goes through a cooling section, and then the product comes out after this. So, in this microwave zone, what they are also doing is, in addition to exposing the product to the microwave, you also have, you can probably see in this picture, the product is going through a zone which is filled with water. So, in other words, the microwave is delivered to the water, and then in turn it goes into the product. So, there's going to be two type of heat transfer happening. One, the product receive microwave, and then you are going to have a volumetric heating. The second, the water where the product is suspended, it receives some heat treatment through microwave, and that raises the temperature, and that heat also going to be transferred into the product. So, that means, let us imagine this is your treatment chamber, this is your pouch, and then this is your water. You are going to send microwave here, it is going to heat. You are going to send microwave to the water, it is going to heat, and then this heat in turn heat the water. So, in other words, they are kind of trying to provide as much opportunity for the product to receive the heat from microwave as well as the surrounding water, so that any non-uniformity in temperature can be reduced, so that you have much more uniform temperature. Because ultimately, remember, in any of the processing methods, you have to demonstrate what is the uniformity of your treatment, how that will help to control the inactivation of microorganisms. So, that is the principle, and in the previously they did not have this concept. So, they were always going to have, in the absence of, for example, the water, you are only heating the product, that means you are going to have a non-uniformity. So, as a result, the FDA always come back, your heating treatment is non-uniform, so it is not acceptable. So, by adding some water in the system, they kind of try to make it much more uniformity. Concept wise, you have a power generator which generates the microwave, and then you are going to deliver through the waveguide, and then this is the treatment chamber. So, the treatment chamber is like, imagine you have a large water bath, inside which you have a conveyor belt, and in the conveyor belt you have these pouches kind of moving through. So, that way the microwave is delivered to both water and the treatment of the pouches, and thereby you can have much more uniform heat treatment. So, this is called MATS. So, this technology probably approved for industrial use around 2010 or 2012 time frame from Washington State University. Now, this is a batch process, because you are processing everything in batch, because you have pouches where you are processing the samples. There is also another parallel development where they have a continuous microwave processing. So, imagine you have the same soup, but instead of packaging the soup, you are kind of pumping the soup, and then you are going to send to a treatment chamber, and this is your waveguide where the treatment is going to occur. So, in this example, your soup may be flowing here, and then the microwave may be applied here. So, that the microwave is applied, and then once you have that, you are going to have a whole tube, and then you have a cooling section, and then you have a aseptic packaging, and so on. So, it is a continuous method of processing. So, any pumpable product like pasta, tomato, sauces and things like that can be processed. Now, this method is commercialized by NC State University, So, for example, they commercialized this for some sweet potato puree, again about 2010-2015 time frame. So, in either case, you have to look at the uniformity of the temperature distribution during microwave processing. This is an example for one of those simulations. You can see that as you pass through microwave, the center portions here heat much more reddish, so that means they are hot, whereas the blue or green, they are at a lower temperature. So, you can see they kind of try to visualize the non-uniformity of heating, and then they relate back to that the food safety. So, whenever you look at the new processing methods, you cannot just work in microbiology alone or engineering alone. The microbiology and engineering need to work with each other, so that you have a safe product. So, this is just a continuous microwave processing, another schematic. So, you have microwave energy is being delivered to the product, and then the cold product in it's heated, and then the hot product is going through the section. Now, when the microwave sterilization pads are now they call that MATS, microwave assisted thermal sterilization, that is the one initially they were aiming for. Once they commercially successful, then now they start using the same concept for pasteurization. Remember, pasteurization is a mild temperature, whereas sterilization is high temperature, much higher temperature. So, in the case of microwave assisted thermal sterilization, they may be achieving temperature in the range of 130-140 Celsius, whereas in the pasteurization they may be achieving temperature about 70 Celsius or 80 Celsius, so that they can achieve pasteurization. So, it is kind of the concept is kind of similar to thermal, except the heat treatment can occur with microwave delivery. So, they are trying to experiment with the ready to eat meal, heat sensitive viscosity products and things of that nature. So, as of now, microwave pasteurization is not widely practiced in the US. Part of the reason is, I think again, a lot of the industrial segments now adapting high pressure pasteurization. So, a lot of the commercial products pasteurized in the US, they are either conventionally heat pasteurized, or they start adapting more microwave, sorry, not microwave, the high pressure pasteurization. So, whereas microwave pasteurization is relatively a new processing technology. Now, normally when you look at temperature distribution, you kind of talked about the thermal diffusivity. So, that is defined by K rho Cp. So, your thermal conductivity, your density, and then your specific heat, these are all play important role. So, these properties also important in the case of microwave processing when there is no microwave applied. But what are the microwave related heating parameters? So, the microwave related heating parameters are they called the dielectric properties. So, microwave heat material in two ways, one with water, the second with the salt. So, water has basically dipolar, and they try to follow the water molecules, the electric field, and they then agitate, and with agitation brings the friction that result in heat being generated. The same way electric fields like salt, sodium chloride, sodium and chloride ions also oscillate, and that produces heat as well. So, this is just to give you how the sodium and chloride kind of try to agitate and creates the friction, and then here the water molecules, how they both have creates friction with the microwave field. So, those are all kind of reasons why it is there. The rate of energy generation per unit volume inside a microwave can be calculated using this relationship 2 pi, the frequency, the electric field, and then you have two parameters epsilon 0, epsilon double prime. So, epsilon double prime, epsilon 0 is the permittivity of a free space, epsilon double prime is the dielectric loss factor. So, we will talk about that in the next slide. So, dielectric loss factor is the ability of the material to absorb wave, how the material dissipate energy into heat. So, there are two parameters. So, I mentioned microwave is like a light waves. So, when you apply microwave, there are a couple of things possible to happen. One, the wave can shine on it and then it can be reflected back. The second, the wave can go inside the product and then it can dissipate within the product, or the wave can just pass through the product without anything. So, like for example, when you take a torchlight, you apply on the table, this table does not allow the passage of light. So, it may reflect, whereas if you have maybe a glass with a blank in the bag, it is going to stay inside, whereas if you have a glass sheet, it allows the passage of light. The same way, food materials either reflect the microwave, like or some packaging material may reflect the microwave, or some food materials could absorb the microwave, or some materials may just transmit the microwave. So, there are different properties. So, that is what we call dielectric loss factor. So, it is kind of even here. So, you have an incident light either reflected, or it is going to be absorbed inside, or it is going to be transmitted. So, each property, each material have certain property, and you are going to characterize them, and then you are going to have certain value you calculate. So, in case of food material, you want the microwave to be absorbed, and then it is going to stay in the food material. So, once it stays in the food material, it is going to agitate the molecule, water molecules, and that produces heat. So, how much microwave absorbed, and then how much of that absorbed microwave is converted into heat. So, those are the things you need to pay attention to that. So, now we are introducing two concepts. One is the relative dielectric constant. So, the ability of the material to store microwave. So, in other words, you kind of shine the microwave on the food and it is going to be stored inside. So, that is your epsilon prime. Second, you have relative dielectric loss factor, ability of the material to absorb wave, and then that is dissipated into heat. So, once it is absorbed, that is converted into heat. So, that is the factor, and you have the values given here for some different type of products. You ranging from epsilon single prime 74 to 1, and then epsilon double prime 21 to 0. So, and then you have a third parameter which is called tan delta, which is basically a ratio of the epsilon double prime over single prime, and it indicates how well microwave is converted into heat. So, that means you have to convert that into heat. So, let us kind of look at here water. Water has value of 8 and then epsilon double prime 10. Ice has a value of 3 instead of 80, the same when you cool down become ice, it is significantly 3. So, that means the ability of the material to store electrical energy. So, ice has less ability to store compared to water. Water has more ability to store microwave. The second is water has a double prime of 10. So, that means it is going to dissipate much more effectively into heat, whereas ice has 0.003. So, in other words, if you are cooking for example, just a vegetable or some product which is in the refrigeration temperature, you are going to heat much more uniformly when you have just water there. On the other hand, you try to take a frozen product and then you try to do the microwave, would you expect the frozen product to reach cooking immediately? It is not. You go through some type of freezing and thawing cycles. The reason is, what you are trying to do is, when you have just room temperature water, let us say this is 25 degrees Celsius, you are going to heat, there is going to be some slight temperature increase. So, you cook the food. Whereas, in the case of freezing, let us say this is 0 Celsius, you are going to be say minus 20 C, you are going to have some type of above freezing, you try to bring the temperature above freezing, and it is going to be slow process, then it is going to rapidly increase the temperature. So, that is the reason the water and ice, they have different dielectric properties. While we are on the same topic, look at oil and the parameters, they are also similar to ice. So, in other words, if I have oil and water, water has much higher dielectric properties, whereas oil has much lower dielectric properties. So, that means they kind of behave like a more ice in terms of absorbing and generating heat with microwave. One key difference between oil and water is the specific heat. The specific heat of oil is, what is the value? Is generally low, whereas water it's about 4.1. So, that means it is much higher. Because of those difference in specific heat, you have to consider, in addition to the dielectric properties, you have to consider the specific heat of water. So, that when you consider overall heating rate of microwaves during oil versus water, you have to take that into consideration as well. The other thing you have to consider here is salt water. When you add salt, the dielectric property is going to decrease, the ability of the material to store the electric energy slightly decrease, but the ability to convert into heat is going to increase. So, in other words, again like Omi heating, adding salt probably help to improve the heating rate in certain ways. So, again you have to kind of study the dielectric properties of different materials when you are formulating microwave heating, so that you can able to adjust your heating rates during microwave heating processes. So, this just gives you the specific heat of water 4.1, whereas you have oil 1.67. So, in other words, water require lot more energy 4.1 kilojoules, whereas oil require less heat energy 1.67 kilojoules energy. So, the heating rates kind of they take a different pathway, even though the dielectric properties of oil is lower than the water. So, the other thing probably going to happen, remember when we talked about electrical conductivity, we talked about how the electrical conductivity and temperature, they are coupled with each other. In other words, when you add certain temperature, it is going to increase the electrical conductivity, which in turn increase the heating rate and then increase the temperature. With the increasing temperature, you are going to increase the electrical conductivity and then so on and so forth. The same way, when you have microwave, At low temperature, when you shine the light on the microwave on the product, the absorption is going to be lower, but it's going to start heating. Then it's going to penetrate more into the product. It's going to heat up the product. Then it's going to absorb more microwave, and then it's going to heat generate. So it's going to keep going. The temperature and the penetration of microwave going to increase. And what's going to happen is you may have different food materials have different absorption capabilities. So that means they are going to heat in different ways within the microwave. So that's the reason why, to avoid that non-uniform heating, in the case of Washington design, they just added water in the mix, so that they are heating the pouches in the presence of water. So you not only heat the product with microwave directly, but you are also trying to use the water as a supplemental heating, so that you maintain certain uniformity of the product. Attenuation factor, it's kind of the decrease in the power on intensity of microwave as it travels through a medium, and it's calculated by this complex equation. So you have the epsilon prime, then delta, and it kind of provides certain value. So let's imagine you are a food processing engineer working for a company which prepare microwavable foods. Then you have to study all these engineering properties related to microwave, characterize them, and then you kind of prepare your microwave foods properly. The another parameter is the power absorption. So the power absorption is in the microwave. So we talked about ice and water. Initially it's frozen, so generally it doesn't able to penetrate much, but once you warm up, you can able to penetrate more in the product, and that generate more heat in the case of microwave, and this is kind of given by this relationship here. The other thing you need to consider, we primarily looked at microwave of food materials. Now, most of the food products packaged in microwavable containers, right, like you may have a polymeric film or things like that. So polymeric films also going to have microwavable characteristics. So that means some films going to reflect microwave, some films allow passage of microwave through them, or some films probably just totally transparent to microwave. So you have to kind of use appropriate film in your package material, so that you can able to get proper things. Let's suppose you are preparing a TV dinner. So what that means is, so for example, you may have some rice and some vegetables, and then you may have some type of sambar or soup type material, all in the same package. Your rice may have certain microwave heating properties. Your vegetables or meat may have certain heating property. Your soup may have certain different heating property. So if you have a film which allow the microwave to uniformly apply to all the three components of the tray, you are going to have maybe one is very hot, another may be slowly warming up, and so when the consumer receiving it, they may have an unpleasant experience, because either they get heat damage, because it's very hot, it harm them, or they may have a not very lukewarm product, so they may not like it. So how do they allow microwave uniformly heating? Is by properly select the films. So you may be using film, let's say the microwave for rice takes more effort, they may allow more microwave to pass through the chamber where rice is there, whereas if your soup require less heat, then they have a different film which only release very little microwave to pass through. So, by selectively controlling the properties of the film, they can make sure that they may just say, okay, microwave this box for 5 minutes. So, at the end of the 5 minutes, all the 3 components going to be at the same temperature because of the design, so that the consumer going to enjoy the product, but they don't need to worry about all the complexities of how to design those things. That is the job of a food engineer or packaging person to come up with the right choices and so on. So, again microwave has a complex temperature distribution. So, shown here you have hot and you have cold and so on. That temperature distribution can be modeled using finite element finite difference methods shown here. So, again you can see that you have a heat diffusion component here, and then you have a heat generation due to microwave, and then this may be some evaporation component, and this is the energy input to the product. And then if you solve for the temperature field, you can find how much heat distribution, and then from there you can be able to establish the uniformity of treatment. So, in terms of critical process parameter, again microwave is a thermal process. So, we always talked about temperature and time is the primary process parameters. In addition to that, you also have shape, volume, surface area, packaging can play a role, and then the geometry of the design of your equipment can play a role. What frequency you are operating, whether or not you have a agitator in the system, are going to play important role. When you are cooking foods with microwave, you can probably, because of the uneven heat, especially when you have high sugar content, you can have scalding effect, because maybe portion of the sugar is going to be get very warm, and that can result in mouth or tongue burn. And similarly, when you have a steam generation in a sealed product, you can generate heat with a lot of steam inside, and then you suddenly open, it can cause burn. So, that is something you have to pay attention to it. One of the things you need to pay attention is microwave and metals, they do not work with each other, because you can create a arcing. So, that means you kind of want to avoid those type of things in the microwave. And when you have styrofoam type of containers, they can probably melt, and again that is something you kind of want to avoid. The microwave, when first introduced in the 40s and 50s, people worried about the microwave safety, whether how affect human health. So, in 1968, Congress allowed the FDA to protect public safety, and then they were testing procedures. So, for example, our house we are using microwave, but those microwave do not expose to the humans, they are contained within the chamber, and they wanted to provide leak tests to make sure that there is no microwave leak out of the microwave containers and so on. The industrial application of microwave is pasteurization, sterilization. It is kind of already more practiced in the Europe, whereas in the US the sterilization just commercially approved, but it is not widespread. It happened in 2010 time frame. So, it is still evolving. Pasteurization research is more coming along. So, the a company in North Carolina, they have been processing sweet potato puree with microwave processing. That is one of the applications. The other applications include some fish processing and things like that. So, it is kind of relatively limited applications there, but there is planning to have more application. Coincidentally, the Tata Corporation in the US, in India, have a partnership with the US company, and they are trying to bring in microwave processing to some processing food in Indian context. So this is kind of provide some examples of microwave heated products, and you have some reading materials you may find useful. Now we can go for some discussions.
Sir, like that additives like salt, can it be used to increase the dielectric loss of low heating foods?
Right, sure. You can probably alter the heating properties of microwave, dielectric properties of microwave using salt, but similar to ohmic heating, you have only so much salt you can add to the formulation. So you have limitation from that point of view.
Okay, and means what is the main mechanism of microwave heating? Means the dielectric or the ionic conduction? Means which one?
So most of the food contain water, so it's a dielectric heating of water probably the predominant, because salt is relatively smaller portion.
Yes, yes.
Right.
Okay, sir. Thank you, sir.
So in microwave heating, if we are heating spaghetti and meatballs, for example, how is it ensured that it is uniformly heated? Because spaghetti may get heated at a different, in a different way.
So you are thinking both spaghetti and meatball in the same zone?
Yes.
Rather than, so under those circumstances, you may have to adjust the dielectric heating properties of either spaghetti or meatball, so that for a microwave they are seen as the same product.
Okay.
So if the dielectric properties are much uniform, then microwave is going to seem as the same thing, and then it's going to heat to the same temperatures.
Okay, because that's the same principle they may apply for those packed lunches, right? Like the tray that is directly put in the microwave and it heats uniformly.
Right.
It heats uniformly.
Right. So the TV dinners, they
Yeah.
have different platforms, right? Like different packets. So one may have rice, another may have a vegetable, another may have. So each has a different zone. So that means you are not probably adjusting the salt anything, but you kind of control through your film. But there are multiple ways of achieving the same goal. You can also adjust the dielectric properties of some of the salt in rice, your vegetables and so on, but you can also do with packaging.
Right, yes. Thank you.
Sir, I have one basic question, that what are the major challenges which we are facing in using the microwave processing at industrial scale, and what could be the remedies?
Right. So microwave technology for industrial applications is kind of slowly it came in only 2010, 2012. Now I think the equipment providers are limited, right? So it's a new technology, so probably at least 2 providers. Europe has more providers than US, so that's probably one limiting factor. Second, you probably have competing technologies, right? So you probably have, at least in the US, more and more consumers are interested in what they call pasteurized products than shelf-stable products. So microwave processing was initially developed as a sterilization tool, whereas I think the consumer interested in pasteurization, and right now that too with the clean label movement and all those things, the consumer want less heat processed samples. So when they look at microwave, probably it's more heat processed. So again, there are industry want to prefer different methods. than microwave processing. So, those are all the complex things, but ultimately look at this as a tool. So, there are products which are heat stable, microwave can be readily adapted. There are products which are heat sensitive, microwave may not be adapted.
Sir, so I want a suggestion from you that as a food process engineer, what are the factors which we can tap in to grow the microwave technology more and to give a better feel to the industry or to the consumer that they can accept these technologies?
So, I think like again the technology adaptation is going to be a slow and nonlinear process, right. I think in other words, doesn't matter how much academic researchers provide information, the industry has many other factors to decide whether they want to use microwave, ohmic heating or some other technology. So, we probably we can give them scientific knowledge, but it is up to the industry to choose which tool to use.
Yes.
So, I think that is probably going to be different depending on whether you have a large manufacturer, small or medium sized manufacturer and so on.
Yes. Sir, would it depend on the customer preferences or the area wise that some as you mentioned that as the USA customer doesn't like this and they want the pasteurized product more. So, it would be the factor that the consumer preference would be affecting the companies and the researchers also?
Right, sure, because a lot of times the consumer drive the industrial adaptation of technologies, because ultimately companies want to deliver products consumer like. So, that means they may be choosing technologies based on some of those consumer preferences.
Okay. So, thank you, sir.
Sir, I have one basic question. In general, if we search the mentally what are the industry they are using microwaves, so we found that microwave dryer and microwave digester is getting more popular instead of microwave decontamination unit. What's your opinion, sir? Why the industry prefer instead of decontamination unit? I know that in case of microwave dryer, it can be very fast as compared to conventional techniques. So, what will be the most probable reason? So, because of that, these two domains are getting more importance rather than decontamination unit. And secondly, instead of like high heat resistance microbes, which can be easily deactivated using microbes, instead of that or whatever the technologies that were mainly used, either it can be ohmic heating or pulse electric feed, they had their own limitation. So, sir, what's your opinion for large scale purpose? So, is there a practical chance to getting absorbed by the industry, or there we need to find out another existing technology which can replace this innovative technologies?
Right. So, let us kind of look at one thing at a time. So, the first thing is microwave drying commonly adapted in the industry. So, if you probably broadly look at the different unit operations, drying is probably one of the most energy intensive processing applications. So, conventional drying takes a lot of energy and so it is much higher energy intensive. So, you have to find a way to reduce energy use in food process applications and so on. So, in that sense microwave is much more energy efficient and then it can also dry samples much faster compared to conventional drying and then you may have a better quality. So, that is where microwave drying, radio frequency drying, these are all getting more popular compared to the conventional drying methods. So, I think that is probably one of the applications. So, the second question is related to which one?
So, sir, what will be the future of this decontamination unit? If we can really rely on microwave decontamination unit, or we want to find something more alternative technologies that can be replaced, which can be commercially viable?
Right, sure. So, again this is a moving target. So, think about this as different tools, because one of the common challenge people do is, and again it's a human nature. So if I'm a researcher spending 10 years or 20 years in my life focusing on microwave, or I'm focusing on high pressure, or I'm focusing on UV, different technologies, I believe that technology is probably can solve all the problems. But in reality, no one single technology can do everything for all wide range of food products. So you have to kind of look at this as a tool. So I have multiple tools as a industry person. I have microwave, I have UV, I have high pressure, pulse electric field. So for this application I may use this, for this application I may use this, but it's going to cost this much, this is going to cost this much. So I have this much budget available, then you choose the appropriate thing.
Sir,
so
is there any country to using this kind of multiple system, or any country industry is currently using this like combination of different technologies on a single unit, processing unit?
So like I think you probably may not use this combination. So there are two separate things. So for example, you may be processing potato soup, you may be using, for example, aseptic processing for potato soup line, whereas you may be drying some material, you may be using RF drying. So it's kind of more product based or category based. But remember, the companies want to maybe have one single technology and then try to use as broad as possible. In that sense, today conventional heating process probably fits that, because they can able to do wide range of products, but it has its own limitations in terms of energy efficiency, water use, sustainability, degradation of nutrients and so on. So it's kind of slow process. So other thing is, the company is going to invest in equipment which is legacy operation. Is somebody is using it for 30 years, 40 years, and the equipment working fine, there's no incentive for them to replace with the expensive unit. Whereas you are a new entrepreneur or new startup company, you want to invest, you rather invest in a new technology than conventional technology, so that you try to get a competitive advantage. So I think those are the type of things you have to make. So it's not purely scientific, but a combination of science and then the business decision needs to come together.
Sir, last question. In 2000, most probably 2019, there was rumors like Japan is going to ban the microwave due to the irradiation. Sir, what's your opinion on large scale point of view? If we use the microwave in in industry, they are using the microwave for like one or two operator will be there to use this microwave. Technically speaking, it's not, theoretically it's not kind of leakage of the microwave radiation, but in practically there also be and some types of risks that can be microwave can be processed for the worker to the. So what will be the safe limit or you can say safe distance to avoid this kind of like injury or irradiation problems?
Right. So as I mentioned in one of the slides, the FDA or the has certain leak test, and I think it's probably more around the prevention. So in other words, they don't want any leaks, so you can probably provide appropriate metal shields and things like that, so that there's no leak of microwave for the household operator as well as the industrial operator. So I think that's probably a simpler way, and you can probably measure the leaks and so on. But I'm not a safety expert for microwave, leak detection, all those things. So maybe you have to look at that appropriate guideline and then make that determination. But normally, as long as you use the appropriate controls, shields and so on, microwave operation is safe to use.
Okay, thank you, sir.
Sir, as you said that in the discussion that conventional technologies are in the product, if we are going with the product, conventional technologies are applicable. But if we are going microwave heating, ohmic heating, they have the specific limitations with the product also. So sir, we can say that this is the main challenge or one of the key challenges that these technologies are not being adopted by the industries.
Can you repeat the question again?
Sir, as you have said that ohmic heating and microwave heating, they have the product specific limitations. But in comparison, the older technology or conventional technologies, they have the limitations such as the environmental barrier or pollution barrier. So we can say that this is giving an opportunity to the entire industries that they are not going to use the new technology.
So again, like a lot of the adaptation of new technology, at least I am talking in the US, it's driven by the consumers.
Okay.
So if consumers not worried about the health and wellness and additive pre-processing and so on, the industry may not have interest in looking at, for example, non-thermal technologies and so on. Whereas with the interest in minimally processing, clean label processing and so on, the high pressure pulse electric field and many of these technologies came in. They were more expensive compared to conventional processes, but you make a product with the less expensive, no consumer is buying, or you make a product, consumer willing to pay more, which one you choose. So usually, like for example, many companies like guacamole, juices and so on, the consumer is willing to pay a little bit more premium for some other products if they think they are getting the appropriate quality. So for example, in juice products, consumers think it has a better nutrition retention. Whether or not actually there, I think it's a little bit marketing, the scientific data is still evolving. That needs to happen in the future. But at the moment, I think that kind of helps the industry to adapt some of the new technologies.
Yes, there is a psychology behind it that if they are getting it cheaper, they would not believe on the nutritional quality and they will prefer the costlier one. Sir, but we can do this for the countries like, sir, we have countries where food nutrition is necessary, like African countries, but we are not able to provide them. And we are today in the world, if we are trying to focus on the sustainability, so we can use this product there also.
So again, food is something each set of consumers going to have different preference, right? So for example, you have US consumers prefer certain type of meals or food products. Indian consumer prefer different, whereas European consumers prefer and so on. So you have to adapt that for your local customer needs and then try to formulate that. So for example, in a different topic, if McDonald's come to US or India, they are not going to sell the same product in the US versus in India. They are going to localize and adapt the local products for the Indian market and so on. So I think that's where you have to consider that. And it's probably difficult for one country to make products and sell to different countries, unless it's a very standard product. So for example, milk. Yes. So milk may be common, so whether it's done in the India or US or Europe, probably you can export to different places, assuming you can able to meet the shelf life.
Okay, sir. Thank you, sir.
Okay, sir, we can conclude here.
Okay, sure. Thank you.